So last time we talked about orbital diagrams. We're going to learn a quicker way to write orbital diagrams, and they're called electron configurations. So an electron configuration is a shorthand for the orbital diagram. The electrons are not shown in specific orbitals, nor are they shown with their specific spins. So rather than drawing all of the electrons out as arrows, we're going to be just writing them in a little bit shorter way. This way is much quicker and is much faster than orbital diagrams, but this is just one of the other ways we're going to discuss. So we're going to start by looking at the orbital diagram of oxygen. So that's the orbital diagram for oxygen. We have a total of 8 electrons there. The electron configuration is using the same information but writing it in a little bit different way. So we're still going to include 1s. So that's the 1 represents the energy level, the s the sublevel, and instead of writing out the electrons, we're just going to write an exponent of the quantity of electrons. So there's 2 electrons in the 1s, so it is 1s2. We don't say 1s squared, we say 1s2. So 1s2, 2s2, 2p4. So notice how all of my numbers are written as exponents, all of my letters are lowercase letters, and all of my energy levels are capital. If there's a couple ways you can check yourself to make sure you have the right values. If you add up all of the exponents, they should add up to the same quantity of electrons. So if we do that for manganese here, it should add up to 25. That's a quick way that you can check yourself. The other thing that can kind of, if you are really into your electron configuration, it's easy to keep going or just and go past where you need to go. So you just want to make sure that you know what sublevel you're going to stop in so you don't go too far. But it's just following the exact same order as before. If you wanted to, you could draw the orbital diagram and then make the electron configuration from the orbital diagram, but you're making a lot more work for yourself. So here's arsenic, ends with 4p3. If you end up comparing like the last one, you want to make sure that you change the last number if you need to. I can't tell you how many times I've seen on a test for arsenic, for example, like this, that they just use the last one and then add something on. Can't do that. You want to make sure your numbers are still adding up. Promethium is a inner transition metal on the periodic table. So it makes it a little bit tricky, so I want to go through that one with you. Promethium is found in the inner transition metals right down here. Promethium right down here is number 61. It is in the inner transition metals. So we start this electron configuration exactly the same as we have before with 1s2. So if you're using the periodic table as your guide, you can physically just count the elements to figure out how many electrons you have. One element would represent 1 electron. So 1s2, 2s2, right there. After 2s2, we go to 2p, which we would have 2p6. After 2p6, we go to 3s2, 3p6. Whoops. You want to make sure your numbers always look like exponents, that you're not just writing this random series of numbers and letters. Then after that, we're going to go to the 4th period. We're going to have 4s2. Then we go down a level to 3d10. Back up to 4p6. Now you might be running out of room on your paper at this point. It is acceptable to start a new row of it, but you want to make sure you're stopping after the exponent. So you could stop, for example, right here after 4s2. You would stop right here because that's where the natural break occurs. So I'm going to continue on. We're going to go to 5s2 down here. 4d10, 5p6. So this part, straightforward. The next part is where it gets a little bit tricky. So we're still going to have 6s2, that's expected. After that, this is where it gets a bit tricky. So we have La, which is lanthanum. That is part of the D block. Now, what ends up happening, why this is split, is it's because of the way the energy levels work out. The energy required for an electron to exist in the 5D is very close to the energy required to be in 4F. So with both of those in mind, it kind of does something weird with the periodic table. Now, we're just talking about the general way to discuss the periodic table. There are a lot of exceptions, which we're going to talk about in a later video. There's a lot of electron configuration exceptions in the intertransition metals. So we're not going to talk about that right now, but just know the way we're learning is the most likely electron configuration. It doesn't always occur. So we're going to have this one element here. This is the 5D1. Because there is only one, we have to write it 5D1. It has to be included. If we don't include this element, our electron count isn't going to be correct. After 5D1, we're then going to go to 4F, which in this case we can count 1, 2, 3, 4, and have 4F4. If I added up all of the exponents, I would have the same quantity that I need for promethium, which is 61. So after writing out promethium, you might be thinking, well, that was a lot of writing, and we were really only interested in the last part. So there is another way that we can shorten this. It's called the noble gas shortcut. With the noble gas shortcut, you can only use this if it's indicated in the problem. You can't just automatically go to this. Sometimes when we give you a quiz or a test, we want to make sure that you understand the principle of writing everything out. Sometimes we want to just make sure you know how to do the last part. The last part is the most important. So that's why sometimes you will use the noble gas shortcut. So in this example, there's lead. Lead goes all the way to 6p. So it's written out here. You can kind of see this helps to illustrate that it's really just one line or one sequence of letters and numbers to help show you the electron configuration. So what you end up doing is you go to the period above. So lead is in the 6th period. It is PB. So you would go to the 5th period and go to the noble gas. The noble gas in this case would be xenon. So I actually wrote out xenon for you, the electron configuration. So if you look at lead from the beginning to 5p6, it's identical to xenon. So what you can do is write it in brackets and then write the remaining part, making it lead. First, let's identify the noble gases. So we have argon for manganese, argon for arsenic, and xenon for promethium. Let's say you had a noble gas, and I asked you for the noble gas configuration for some reason. So let's say I asked for krypton. So even if I asked you for the noble gas shortcut of krypton, what you would do is you would go up to argon. So you'd have argon in brackets and then write out the remainder for your noble gas. So you always go up a period all the way over to the noble gas group. So here's what you end up with. These are the same ones as above. You're just shortening them with the noble gas. So in the last one, we were looking at valence electrons. There's a few more. In this example, we're looking at something called the valence configuration. So if you think back to the valence electron, those are the electrons on the outside of the atom. So with the valence configuration, we're going to show what electrons are in the outside. So we would take a look at the energy level. We would pick, you always end up with S and sometimes P, but you never have D or F. So in this example, we have bromine. So the S and the P are going to be included in my valence configuration. So once you have your valence configuration, you can add it up, add up your electrons, and in this case, bromine has 7 valence electrons. So we're going to try this for the remaining ones. So for silicon, I like to start with the noble configuration, noble gas configuration. So we would have neon, which ends in the 2nd period on the periodic table, and then we would go to 3s2, 3p2. So that's my noble gas configuration. My valence configuration then is taking the highest S and P from that. So my valence configuration would be 3s2, 3p2. So how many valence electrons do I end up with? Well, in this case, I end up with 4. So I add 2 plus 2 to get 4. Uranium is a bit tricky. Uranium is number 92 on the periodic table. So you're going to use the noble gas of radon, which is Rn. Go 6s2, 5d1, 4f3. Okay, so you do need that 5d1 electron in order to have the appropriate noble gas configuration. Did you catch that? It should be 7s2, 6d1, and 4f3. This is a common mistake that students make on tests. So we have 7s2, 6d1, 5f3. So we only need the ones in the highest energy level, which in this case is 7s2. So my valence configuration for uranium is just 7s2. That's it. The D and the F are in lower energy levels, so they're not going to be on the outside. So that means that uranium has 2 valence electrons. So let's take a look at lead. Lead is number 82. We're going to use xenon like we did on the last page. Xenon 6s2, 4f14, 5d10, 6p2. So for lead, there's actually a second way that you can write it that is accepted, and that is splitting up your D block. So you could also have written xenon 6s2, 5d1, 4f14, 5d9, 6p2. Either of these would be accepted. The one in blue or the one on top is the more correct one if you have to pick one, but on a quiz or a test you could write either. The big thing is you have to make sure that both D's added together add up to the same thing if they were together. So with lead, we just want the S and the P for the valence configuration, so we'll have 6s2, 6p2, giving us a total of 4 valence electrons. Keep in mind that a lot of the transition metals only will have those 2 electrons because they only have the s electrons in the highest energy level.